Okay, so what we have left is exam 5, the final. There you have two options of when you can take it. You can take it Monday with the night class. So that would be the 17th. And the room would be 26. So not this room, just one room over. And then the day class is Thursday, 12:20 at 2 p.m. in this room. And the topics are going to be everything up through conservation of mechanical energy. Okay, so there are practice problems on D2L for a topic after that. That's rotational kinematics and rotational kinetics. It says two sets of problems. It's all kind of the same thing. And so I am hoping to have some time to talk about that. Maybe it'll just be on Thursday. For the people who are not taking Physics 2 and are not trying to get ready for like a standardized test on physics, like that, some people are getting ready for the MCAT or something like that, or the PCAT. Those people probably want to get a little introduction to this topic. It will come up in Physics 2. And so I'll talk about it some on Thursday, and I'll also on D2L put up some old lectures on that stuff. So if you want to go through it, you can. But those topics will not be on the final, so you don't have to do any problems to get ready for it. It's just for the people who are going to go on after this. Yes. I don't remember what it's called, but it's like angular kinematics and angular kinetics. It has to do with torques and angular accelerations and stuff. Yes. I will also, if you come in, anybody who comes in with homework questions, I'd be happy to answer homework questions as long as you want. I'll ask for that today too. But yeah, I'm not gonna introduce any new stuff that's relevant for the exam. Yes. Game time decision. Yeah. You can come in and just like check out the atmosphere and just be like, this isn't for me. I'm going to make it a touch longer than the other exams, not too much. So I would say maybe 6 questions of about the same level as the questions on the other exams. Maybe it'll be more sort of like intended to be like an hour and a half exam compared to an hour exam. Yeah, that is not. So conservation of mechanical energy, the stuff we finished talking about last time. I mean, I'll go through some examples today, but that's the last stuff on the test. And so the angular stuff, the stuff that comes after that is only relevant for the people who are trying to get ready for stuff outside of this class, either Physics 2 or some physics test that you have to take for admission to a professional school or something. Yes. Yeah. Yes. But the weight is the same, yeah. Anybody have any other questions about the test? Yes. Yes. Yep, that's for sure the best way. And what I would recommend doing, like assuming that nobody is going to have time to go through to do every problem in the whole from the whole semester, I would recommend starting at the beginning and like go through all the problems, but don't solve them all. Just ask yourself, do I know the steps for this? And if right away you're like, okay, I do this, I draw this, then don't spend a lot of time on that one. Just move on to the next one until you get to the ones that feel rusty, you know, and then spend the time on those. Yes. Yep. It's so the questions will be just like the questions on the old exams. They'll just be a couple more of them than on the other exams, and it can be anything from the whole semester. Yes. It's going to be weighted more heavily on the newer stuff than on the older stuff. Uh, maybe 50-50, or maybe 2/3 from the whole semester and 1/3 from the new stuff, something like that. Any other questions? Yeah, somewhere in the 50-50 range, you know. Any other questions? Well, let's do a couple energy example problems. Why don't I do the first one, and then after that, I'll give you guys time to work on the second and third ones before I go through them. So let's say um, there's a skier going across a flat ground with a speed v, and uh, once he gets up to the base of this hill, he starts going up. So a skier has speed v across the flat. Um, and makes it to a maximum height of 2.0 meters up the hill. Okay, so he has some speed along the bottom, starts to go up the hill, slows down as he goes up the hill, reaches a highest point that's 2 meters above the flat. We're talking about a vertical distance. That's important. We're not talking about a distance along the hill. So this is 2 meters. If there's no friction, what was the speed along the flat? Okay, so the first thing we have to do is make sure that conservation of mechanical energy applies in this case. To do a problem using conservation of mechanical energy, uh, there can't be any non-conservative forces that do work. Okay, so what forces are acting? Let's just think about what forces are acting. Like what would be on a free body diagram of this skier? There's a weight force, that's conservative, and a normal. Those are the only two. Um, the normal force doesn't do any work, and uh, so conservation of mechanical energy is going to work in this problem. Um, yeah, so to use conservation of mechanical energy, um, no non-conservative forces can do work. The forces that are acting on the skier, So here's a free body diagram of the skier. There's a weight force and a normal force. The weight force is conservative, so that's fine. The normal force is non-conservative, so that means it could cause a problem. But last time I talked about how normal forces and centripetal forces in circular motion, even though they're non-zero forces, they do no work. So we're fine here. Okay, so we'll set it up. Calculate the potential and kinetic energy at instant 1, and calculate the potential and kinetic energy at instant 2. Yep. It doesn't ever do work. In a rolling or a sliding problem, it never does work. So even though that's a non-conservative force, it wouldn't show up in energy analysis, and so it's fine to use conservation of mechanical energy. That's true of normal forces in sliding and rolling, and it's also true of centripetal forces, forces toward the center of a circular motion. Mhm. Exactly. Yep. So at every instant, the velocity vector is perpendicular to the force, and so it doesn't do any work. This is in a vacuum, so it's fine. But because of air resistance, you mean? Oh yeah, no, it looks like no, that's all one. Yeah. Okay, so first, gravitational potential energy. That's equal to his mass times 9.81 times the height. And in order to come up with a height at that instant, we have to choose the height equals 0. Might as well choose this to be our height equals 0. You can choose it anywhere. You just have to be consistent with it through the whole problem. So that's mass times 9.81 meters per second squared times his height at instant 1. Instant 1 is while he's moving along the flat, so that's 0 height. So there's no gravitational potential energy. And now the kinetic energy along the flat is 1/2 times the mass, and we weren't given the mass. We're going to see that it just cancels out in the end, so I'm just going to leave it as m. Times the speed squared, which we don't know. So I'm just going to have to leave it like this, just 1/2 mv squared. And now instant 2 is when he reaches the highest point on the hill. So the gravitational potential energy is mass times 9.81 times the height. What's the height? Yep, 2 meters. And then the kinetic energy is 1/2 times the mass times the speed squared. What's the speed when he reaches the highest point? 0. Yep, that's when he comes to rest just for an instant before he starts moving back the other way. So 0 squared, and so this is 0. And so now conservation of mechanical energy. Add up the energies at instant 1. You get 0 plus 1/2 mv squared is equal to 19.62 m plus 0. And now you can see you can divide both sides of this equation by m, and the m's just go away. What that says is it doesn't matter what the mass is, we'll get an answer that would be true for any mass. Multiply both sides by 2, and you get v squared is equal to 39.24. And now take the square root, and the speed is plus or minus, what's the square root of 39.24? 6.264 meters per second. This is a speed, so we want the positive one. So in order to make it 2 meters up the hill, the speed on the flat has to be 6.264 meters per second. And I mentioned this before, but it's important to notice we are just talking about the change in height, okay? We're not talking about the distance up the hill. So we don't know anything about how steep this hill is or how shallow, it is. As long as there's no friction, this would all be true whether this went up steeply to 2 meters and he reached 2 meters of height here, or whether it went all the way out and it took him a mile to get out there. This would all still be true. Although if he was going to travel a mile to get a height of 2 meters, it would be a lot less likely that you would get good results by assuming no friction, because that's just being subjected to a small amount of friction for a really long time. Okay. Any questions about that one? Okay, what do you think would happen now if instead of starting out going 6.26, 6.26 meters per second and ending up at rest up here, the skier started at rest here, went down the hill, and then was going some speed on the flat? What do you think the speed would be on the flat? It's a speed, so it would still be positive. Yep, it would be going the opposite direction with the same speed. And the reason that it works out that way is, notice all you would be doing is exchanging which one of these was instant 1 and instant 2. You'd just be switching what side of the equation you put stuff on. The skier would be starting with a height of 2 meters and no speed, and would be finishing with a height of 0 and this speed. And so the equation works out the exact same way. Okay. In other words, there's something important about this energy approach. You don't know anything about which thing happens first, which thing happens next. It doesn't know that. It just knows that if you exchange position for speed in this certain way, these are the two possibilities. Okay, now let's do another one. And let's do a thing where someone starts on a hill on skis or whatever. And let's say the hill has a height of 3 meters. And down at the bottom of the hill, the person runs into a barrier that's attached to a spring. Okay. And let's say that the spring constant, K, is equal to 400 newtons per meter. Actually, let's make it a little stiffer than that. 600 newtons per meter. How far will the spring compress? Okay, so the potential energy functions you're going to need. There's gravitational potential energy, that's mgh. And then there's spring potential energy, that's 1/2 times the stiffness of the spring times x squared. And that x is the spring's distance from its resting length, how much it's stretched or compressed. Okay, so try to follow along, think about it just in the same steps as the example I just did, and see if you can work through this and figure out how much that spring is going to compress. Now, there's not just going to be one type of potential energy. You're going to have to, there's going to be gravitational potential energy and spring potential energy at each of these instances. Okay. So see if you can think through that. And then after I give you a little time to work on it, I'll go through it. Through this. Okay, so first you have to think about whether conservation of mechanical energy applies. And it does, because the only non-conservative force is a normal force. So instant 1 is going to be at the top of the hill. And instant 2 is going to be when the spring is compressed as much, at maximum compression. So first, at the top of the hill, gravitational potential energy. Oh, we need to know this guy's mass. Dang it. Sorry. Let's say 40 kilograms. What? It's not because of the spring. There's no mass in the spring potential energy. So we have 40 times 9.81 times the height, and might as well call this our h equals 0 at the bottom of the hill. So that's times 3. And that gives you 1, 2, 2, 6 point something. Is that right? 117. Yeah. Point what? Okay, and then the spring potential energy at instant 1, what's the compression of the spring? How far is the spring from its resting length? Yeah, 0. And then at the top, there's no kinetic energy because the speed is 0. And then at instant 2, what's the skier's height? 0, so this one comes out to be 0. The spring potential energy, so that's 1/2 times the stiffness, 600, times how far the spring is from its resting length squared. Do we know what that is? No, we're trying to find that, so I'm just going to leave that in here as x squared. And then do we know the speed? If that's the point where, if that's the farthest the skier goes with the spring, then at that instant the speed is 0 before the spring starts pushing him back the other way. So this is 1/2 times 40 times the speed is 0 squared, so 0. The, the what? Oh, that's just the units. So we'll put units back at the end of the problem, but you don't have to carry it through. Okay, so 1177.2 plus 0 plus 0 is equal to 0 plus 300x squared plus 0. And so 3.924 is equal to x squared. And so x is just under 2. What do you get? 2 point, yeah, 1.98, and that's meters. Ooh, that's a lot. That has to be a pretty long spring to compress that much without, you know, the coils of the spring hitting each other, and then it stops acting like a spring. But you could make one like that. So it's kind of cool how it works. Like if you have a problem where this is applicable, you can do a very quick, easy analysis that relates an object's speed to its position. In this case, the speed was in sort of a middle region, but we could go in and calculate the maximum speed or whatever if we wanted. Yep. So whenever the spring is at one of its endpoints, so it's either stretched at its maximum or compressed at the maximum it's going to be, the speed is 0 at those instants. But let's do another spring problem now and calculate the maximum speed. So let's do one where you have like a little cart with little wheels attached to a horizontal spring, and you pull it back and let it go. What do you think the spring would do? What do you think the system would do? Can you imagine? It's gonna, so it would spring this way, go past its equilibrium point, and then the spring would start to slow it down, and it would just keep doing this. So let's do a calculation like that. Yep. Then you can do problems like that if you have a way to calculate, or if you're given the work that's done by the non-conservative force. But we're not going to do any like that. Okay, so let's say there's a spring attached to this wall. And let's say this has a mass of 1/2 kilogram. And let's say the spring constant is 300 newtons per meter. So if you stretch the spring .1 meters from its resting length. First, what's the speed of the mass at its fastest point, the greatest speed of the mass. And then this isn't something that you have to do in problems, but I'm going to graph, draw a position versus time graph of this motion so you can get a sense of what happens. Draw. Okay. Well, what forces are acting? So let's make sure that you can apply conservation of mechanical energy. Weight is acting. There's a spring force, and then there's a normal force. So this works fine. And the height never changes. So we might as well choose our h equals 0 to be at the height that mass is always at, and then the gravitational potential energy is always going to be 0. So instant 1 is going to be with the mass at rest and pulled 0.1 meters from the resting length. So the x value is going to be 0.1 or negative 0.1. It doesn't matter. You can treat that as a distance or a displacement because that x is squared in the equation, so it comes out positive when you square it anyways. So that's instant 1, and then instant 2 is going to be when it's at the greatest speed. So the gravitational potential energy at instant 1, h is 0, so this is equal to 0. The spring potential energy is 1/2 times 300 times 0.1 squared. And so that is 1.50. That is how far it's stretched from its equilibrium position, its resting length. And then the kinetic energy is 1/2 times the mass times the speed squared, which is 0, so no kinetic energy. And then at instant 2, the height is still 0, so the gravitational potential energy is still 0. The spring potential energy, we don't know where, like how long the spring is at its fastest. Does anyone have a feel for what it would be, a guess? 0. Yep, it's going to be going its fastest as it passes through that middle position where the spring's at its resting length. Because the spring's going to be speeding it up until that point, and after that point, it's going to be slowing it down. So if we knew that, we could type in 0 for our x, but let's just leave it as x and just see what we can figure out. Yeah. So the spring potential energy is going to be 1/2 times 300 times x squared. So 150 x squared. And then the kinetic energy is 1/2 times the mass of 0.5 times v squared, and we don't know what that v is. So 0.25 v squared. Okay, so conservation of mechanical energy says 0 plus 1.50 plus 0 is equal to 0 plus 150x squared plus 0.25 v squared. And we want to solve for v. We're going to come up with an expression that still has x in it. And so we'll be able to use that to figure out what the x is where v is at its biggest. Okay, so I'm going to subtract 150x squared from both sides. We get 1.50 minus 150x squared is equal to 0.25 v squared. Now I'm going to multiply both sides by 4 and just switch sides. So we have v squared over here is equal to 6 minus 600x squared. And now take the square root of both sides, and you get v is equal to the square root of 6 minus 600x squared. And this is positive. Okay, so what this tells us is it tells us for any x value we choose, so we can choose how far the thing is away from the spring's resting length. This tells us what the speed will be. So we have 6 minus something that's always positive. Okay, like notice that whether x is positive or negative, we square it. So this term comes out positive, right? And we're subtracting it. So there's no way for the thing inside the square root to ever get bigger than 6. You see that? If you choose negative 0.1, positive 0.1, anything, any value for x, whether it's negative or positive, makes this number inside the square root smaller than 6. So the biggest you could get is when x is equal to 0. And that says that the fastest this goes is when the spring is at its resting length and the speed is square root of 6. So the biggest this can be is when x is equal to 0, and at x equals 0, the speed is equal to square root of 6. And that occurs when the spring is at its resting length. Any questions about that? Okay, so what would this motion look like? So let's say that this is the position of the mass, and this is time. And if you think of So if we say the 0 position is when the spring is at its resting length, and call this positive, and if you stretch the spring to start 0.1 meters, you're pulling the mass back to a x position of negative 0.1. You see that? And this graph would look like this. It would start at a position of negative 0.1. And it would oscillate between negative and positive 0.1. And because there's no friction, nothing to strip energy away, according to this, mathematically, it would just keep doing this forever. So it's just going, so it's going from 0.1 meters this way to 0.1 meters on the other side of the spring's resting length, just back and forth. And every time it goes through the resting length of the spring, it has a speed of square root of 6, and that's the fastest it ever goes. Okay. So now let's do one where a spring is hanging vertically. And let's say that the object has a mass of 0.2 kilograms, and the spring stiffness is 400 newtons per meter. And let's say that the spring is held at its resting length and released. So what do we want to find out? Yeah, okay, so yeah, let's figure out what's the maximum speed, and let's figure out and then I'll just graph the position versus time again, and we can see what the range of motions is. Okay, so first of all, we have to make a distinction now. Like in this case, think of the horizontal case. The springs, so the spring's resting length is the length that the spring has when it's just sitting on the table, nothing's attached. That is also the length that the spring would be at when this mass is just sitting here at rest. Okay. But when the spring is vertical, that's not true anymore. Because if you have a spring that, like, just sitting on the table is 5 centimeters long, okay, and you hang a mass from it, the mass is going to stretch it a little bit. Okay? And so there are two things we have to think about. One is the resting length of the spring, the length that the spring is sitting on the table. And the other one is the length that the spring is in equilibrium in this setup. Okay. So notice for a vertical spring, we have to make a distinction between the spring's resting length and the length of the spring at equilibrium. Let's say hanging equilibrium. Yes. Well, then they let it go, and that's when we start doing the calculations. Yes, at the rest length where the spring doesn't have any potential energy. Well, if you started it at the hanging equilibrium, it wouldn't go anywhere because that's just where. So what we're doing is so the spring on the table is say 5 centimeters long, and we attach it to the ceiling, hold it at 5 centimeters long, and then when we let go, the mass is going to stretch it out and it'll oscillate. Okay. Anybody have any questions about that? Does that make sense? Okay. Somewhere in the middle. Yep. We can use conservation of mechanical energy because all we have is a weight force and a spring force. There's no normal force or anything else. So there's instant 1 and instant 2. And the way we're going to set it up is we're going to choose our h equals 0 the spring's resting length. The reason we're going to do that is it lets us use this variable h both as the h for the gravitational potential energy and the x for the spring. Okay, so we get it down to a single variable. So then h is the height for the gravitational potential energy, and it's also the x for the spring potential energy. Because if your h equals 0 is when the spring's at its resting length, then if you go to a height of 0.1 meters, you've also deformed the spring 0.1 meters. So that h works as two different things. Oh, right. No, yeah, so it'll work fine for both of those. So the gravitational potential energy at instant 1 what's h at instant 1? 0, yep, so this is 0. So now the spring potential energy, that's 1/2 times stiffness of the spring. What was that, 300? 400? And what's x? 0, yep. So 0 squared, so this is also 0. And it's being released from that position, so the speed is 0, so there's no kinetic energy. And then at instant 2, the gravitational potential energy. Now, what we're going to do is we're going to leave the height at instant 2 represented as h, and the speed at instant 2 represented at v. And again, we're going to see a relationship between the height and the speed, just like we did in the last one. So the gravitational potential energy is 0.2 times 9.81 times h. So that's 1.962 h. And then the spring potential energy is 1/2 times 400 times h squared. So that's 200 h squared. And then the kinetic energy is 1/2 times 0.2 times the speed squared. So that's 0.1 v squared. And then conservation of mechanical energy. Yes. Yes, thanks. The x is our h. So that's when you set it up. So when the spring is hanging vertically, if you choose your height equals, you always want to choose your height equals 0 to be at the spring's resting length. And then h works as both x and the h. So we get 0 plus 0 plus 0 is equal to 1.962h plus 200h squared plus 0.1 v squared. So negative 200 h squared minus 1.962 h is equal to 0.1 v squared. And now multiply both sides by 10, you get negative 2,000 h squared minus 1.962 h. Yeah, 19.6 is equal to v squared. And so v is equal to the square root of negative 2,000 h squared minus 19.62 h. Okay, so this is an equation that tells us, so now if we choose for a positive h, we're moving above the resting length of the spring. For a negative h, we're moving below. And this tells us the speed at any one of those heights. So how are we going to use that to figure out? Well, anybody have any questions about what we have here? Okay, so I think the easiest way to make sense out of this is let's choose the 2 points where the speed is 0. Okay. Then we're just finding where this quadratic thing is equal to 0. Okay. And that'll tell us the two endpoints, like one is going to be the starting point that we know of, and the other one is going to be the other place where it comes to rest just before it turns around. Okay. So there are going to be two roots to this. So let's set v equal to 0. That's the highest and the lowest point in this motion. Okay, well, if v is equal to 0, that means that this has to be equal to 0, negative 2,000 h squared minus 19.62 h, and has to be equal to 0. And you can factor out one of these h's, and you get, let's factor out the negative 2. So negative h times 2,000 h plus 19.62 is equal to 0. So there's two solutions to this. The first one is h equals 0. Well, we know that the speed has to be 0 at h equals 0 because that's where we're releasing it from. But the other one is negative 19.62 divided by 2,000. Can someone divide that? Tell me what that is. Oh, I know what that is. It's 0.00981, right? Yeah. Negative 0.00981. And so the spring is going fastest at the midpoint between, so it's going the fastest at halfway in between these two. Okay, so to plot a position versus time graph, it would start out at the position 0. And it would go from there down to the position negative 0.00981. Just repeat that motion. And exactly at the midpoint is where it's going the fastest, and that's also happens to be the equilibrium position of the mass, where it would just hang. Yes. Mm-hmm. So I factored out a negative h, and now there are only two ways that you can make. So two things multiply together. There's only two ways to make it zero. That's to either make this zero or to make this zero. The two things that are multiplied together. And so one of the roots is if this h is zero, and the other one is if the thing in parentheses is zero. And the only, so solve for 2000h plus 19.62 is equal to zero, and this is what you get. Any other questions? Yes. What happened to the square root? Mm-hmm. It says like mm-hmm. Square root. Yeah. Okay. So if you're setting the square root of, to set the square root equal to zero, you just set the thing inside the square root equal to zero, because square root of zero is zero. So it was just easier to think of it that way. Yeah, right. No, but I guess what I want you to know is if you do have a problem with a vertical spring, set your h equals zero to be at the spring's resting length. So that's always the way to do it. And then that h represents both your x and the h for your gravitational one. But the questions I would ask you would not be complicated like this. I guess I was trying to show sort of like some general stuff about it, but um, it would just ask simple questions like what um, what is the speed of this mass when it's 0.05 meters from the resting length or something, you know? And then you just, then right from the start, you would know at instant two that your h value is 0.05. You just plug it in and solve for v. Any other questions about this? Okay, let's stop there.